Ever wondered how AI systems like GPT or AlphaFold achieve such mind-blowing performance? The answer lies in the intricate dance of neural network architectures, optimization techniques, and mathematical principles that form the backbone of modern machine learning. Today, we're diving deep into the latest breakthroughs in AI research, exploring how transformers, attention mechanisms, and distributed training are reshaping the field. Let's get technical. Let's start with the foundation, neural network architectures. Traditional models like CNNs and RNNs were revolutionary, but they hit bottlenecks when dealing with sequential data or long-range dependencies. Enter the transformer, introduced in 2017 by Vaswani et al., which replaced recurrent layers with self-attention mechanisms. This allowed models to weigh the significance of different words in a sentence dynamically. For example, in a sentence like, "The bank will close at 5 p.m., the model distinguishes between bank as a financial institution and bank as the riverbank based on context. This is achieved through query, key, and value matrices, which compute attention scores via dot products and softmax normalization. The result? Parallelizable, scalable models that outperform their predecessors on tasks like translation and text generation. Now let's unpack attention itself. At its core, attention is a weighted sum of values, where weights are determined by the compatibility between queries and keys. In multi-head attention, the model splits the embedding space into multiple subspaces, allowing it to capture diverse relationships. For instance, one head might focus on syntactic patterns, while another detects semantic nuances. This parallel processing is why transformers excel at understanding complex, multifaceted inputs. But here's the kicker. The attention matrix's size grows quadratically with input length, which is computationally expensive. Recent advances like sparse attention or linear attention approximations, such as the Performer model, address this by reducing complexity from ON2 to O, N log N, or even ON, enabling training on longer sequences without sacrificing performance. Scaling AI models isn't just about adding more layers or parameters, it's about distributed training. Modern systems like DeepSpeed and Megatron-LM leverage data parallelism, model parallelism, and gradient accumulation to train massive models across thousands of GPUs. But how do researchers determine the optimal scale? Enter the concept of scaling laws, empirical relationships between model size, data quantity, and compute resources. Studies show that, up to a point, increasing parameters and data leads to proportional gains in performance. However, this isn't a free lunch. The marginal gains diminish and energy costs skyrocket. Researchers are now exploring efficient scaling strategies, such as neural architecture search, NAS, and knowledge distillation, to balance performance and sustainability. Finally, let's look at the cutting edge. One exciting area is neural differential equations, which model continuous time dynamics for tasks like time series prediction or physics simulation. Another is the rise of foundation models, large, general-purpose models trained on diverse data that can be fine-tuned for specific tasks. But the real game changer? The integration of symbolic reasoning with neural networks. Projects like AlphaGo's Monte Carlo tree search or the recent work on neural-symbolic systems aim to combine the flexibility of deep learning with the rigor of formal logic, paving the way for AI that can reason, explain its decisions, and generalize beyond its training data. So what's the takeaway? AI isn't just about bigger models. It's about smarter architectures, efficient training, and hybrid approaches that bridge the gap between data-driven learning and human-like reasoning. As researchers push these boundaries, the future of AI promises to be more powerful, interpretable, and impactful than ever. If you want to stay ahead of the curve, keep exploring these concepts, and don't forget to subscribe for more deep dives into the science behind the tech. Until next time, keep questioning, keep learning, and stay curious.